So our job here is to anti-differentiate this, meaning we want to find the functions or the function whose derivative is all this. And before we can do that, there's one thing we really need to do. I really want to rewrite this so that this looks like a power of x. Instead of x to the fourth, the fifth root of x to the fourth, I want to write this as x to the 4/5 power. Because powers are easy to anti-differentiate. And then this is still secant squared of x. This is still 7. And now my job is I am looking for a function whose derivative is each of these pieces. So I know that the derivative of x to the fourth has an x cubed in it. But it's not exactly x to the fourth. Because the derivative of x to the fourth is 4x cubed. And I don't have a 4 as a coefficient. So it's not just x to the fourth, it's actually x to the fourth divided by 4. Or if you prefer, you could also write 1/4 times x to the fourth. It's the same thing. Some people like it this way, some people like it the other way. I should also point out, depending on your teacher, some people use the notation of a capital F for the antiderivative. So if your function is a lowercase letter, your antiderivative is the same uppercase letter. That's kind of a standard notation. So the same sort of rule applies for any power of x with one small exception. It definitely applies here. The antiderivative of x to the 4/5 is a power that is 1 larger. So it's going to be x to the 9/5. And my 5s never look good. But then if I took the derivative of that, I would have 9/5 times x to the 4/5. And I don't want that 9/5. So I have to divide by 9/5. The next one really just asks, do you know your trig derivatives? Do you know a trig function whose derivative is equal to secant squared? It's definitely one of them. It's tangent. The derivative of tangent is secant squared, so the antiderivative of secant squared is equal to tangent. And then finally, whenever you antidifferentiate a constant, you get that constant times x. And then we have to tack on a plus c. So this is not quite simplified as much as I would like it to be. It's almost there. What we need to do is we need to simplify this term here. So instead of dividing by 9/5, I want to write this as...
James?
Yes?
I think the 9/5 is supposed to be 4/5.
It's not.
It's not.
So here's what happened. So we'll use this to kind of jump off and talk about the general rule. So when you antidifferentiate x to a power, you end up increasing that power by 1 and then dividing by the new power or multiplying by the reciprocal of the new power. So the same thing is happening here. When I antidifferentiated x to the 4/5, I increased the power by 1. And 4/5 plus 1 is 9/5. And then I divided by that same new power.
Okay, that makes more sense. Thank you.
And what we're going to do is we're going to check our work in just a second by taking the derivative of the whole thing to make sure it actually is what we think it is. Sophia, I saw you had a question.
Yeah, is this on the list of like the one where like it has the rules like on the left and then the rules on the right?
Totally, yes.
Thank you.
You're welcome. So this is going to be 1/4 x to the 4th plus, I'm going to write this as 5/9 times x to the 9/5. And then we've got plus tangent of x plus 7x plus c. And this is the antiderivative. And now we're going to check. Now, the problem with checking an antiderivative is if you're making antiderivative mistakes, you're probably making the same kind of derivative mistakes. So although you can always check to see if a derivative is correct by taking the, you can always check an antiderivative is correct by taking the derivative. It still relies on our ability to take the derivative correctly. So if I take the derivative here, the derivative of 1/4 times x to the 4th is 1/4 times 4x cubed. The derivative of 5/9 times x to the 9/5 is 5/9 times the derivative of x to a power. Well, the power comes down and you subtract 1 from the power. So x to the 9/5 minus 1 is our new power. The derivative of tangent is secant squared of x. The derivative of 7x is indeed 7. And the derivative of a constant is 0. And then if we simplify this just a little bit, we see that 1/4 times 4, those cancel. So we get x cubed. 5/9 times 9/5, those cancel. And you get x to the 9/5 minus 1 is 4/5. And then we get secant squared of x. And we get 7. And so we see that, oh yeah, this actually is the antiderivative of this, because if you take the derivative again, you get back to where you started. Or in other words, if we take an antiderivative and then the derivative, we should end up back where we started, because they should be things that undo each other. They're what I think of as inverse processes. If you do one and then you do the other, you end up back where you started. I think, let me take a look here at one thing very quickly. Sure. So something that we should probably focus on a little bit are the rules. So if I was going to find the, say, antiderivative of x to the 6th, well, I'm looking for a function whose derivative is x to the 6th. And I know that when I differentiate a power of x, I get 1 less in the power. So I'm looking for something like f of x equal to x to the 7th. But I know that's not quite right, because if I take the derivative of that, I get 7x to the 6th, but I only want an x to the 6th. Fortunately, adjusting for multiplication by a constant is a really easy thing to do. If you want to have or to not have a 7 here, you can not have a 7 by dividing everything by 7. So if I divide this by 7 and this by 7, then it works, right? The derivative of x to the 7th over 7 is 7x to the 6th over 7, which is just x to the 6th. And then I should point out that typically our antiderivatives, if they're general antiderivatives, should have a plus c, because you could actually have any constant here and the derivative of the constant would be 0. So here's the general rule. The antiderivative of f of x equal to x to the n is capital F of x equal to x to the n plus 1 over n plus 1. So when you differentiate x to a power, you bring the power down and then you subtract 1 from the power. When you anti-differentiate x to a power, you first add 1 to the power and then you divide by that new power. So it's literally the opposite steps in the reverse order. And then plus c. And this rule is true with one exception. There is one value, there's one power where this doesn't work out so well. What is that?
E?
What's that?
Is it E?
It's not E. E is a perfectly fine number. So I think you're thinking of e to the x, which is a little bit different than x to a power. So what value, if I look over here, what value of n might be problematic? Like, what do I not want?
Is it when it's -1?
Exactly, right? If n was -1, we'd end up dividing by 0, which is not good. So this rule is true, except for when n is equal to -1. Which I kind of think brings up the question, well then, what about -1? If f of x is equal to x to the -1, which is the same as 1 over x, what's the antiderivative of 1 over x? What's a function whose derivative is equal to 1 over x?
The natural log.
Exactly. So the antiderivative, I'm going to say this for the moment, is the natural log of x plus c. Now, it's actually slightly different than that. And I'll tell, so I'll tell you what it is right now. The actual antiderivative is actually the natural log of the absolute value of x plus c. And the reason for that is really just a domain reason, that this function, 1 over x, has a domain that is everything except for 0. And usually the antiderivative should have a domain that's at least as big, sometimes even bigger. So we didn't want to lose part of the domain by not having x being able to be negative. And that's why this absolute value kind of needs to be here. It's also because the derivative of this actually is still that. And I'm going to show you that now because it's something that I think you should see, although I don't think it's something that's super duper important to retain. So I just want you guys to believe that it's true. And then we'll move on to some more examples. So the derivative of the natural log of the absolute value of x. Absolute values are terrible when it comes to really anything about continuity or differentiation because, because absolute values are kind of piecewise functions, right? If you look at y equal to the absolute value of x, which looks like this, really it's that y is equal to positive x when x is positive, right? Here's y equals x over here, and y is equal to negative x when x is negative. And then you can include 0 in either of the sections, it doesn't really matter. So it's this weird kind of piecewise thing where if x is negative, take the negative of that to make it positive. And if x is positive, just leave it alone, it's already positive. We're going to do the same sort of thing here. So we're going to break this up into a piecewise derivative. It's going to be the derivative of the natural log of just x if x is already positive. Right? If x is positive, then x is just x. It's going to be the natural log of negative x if x is negative. Right? If x is negative, then negative x is positive. Now, I'll remind you that the domain of the logarithmic function is x has to be positive. So we're safe here, right? Here, the argument is positive. Here, the argument is positive. But we don't include 0 because you can't take the natural log of 0. Sophia.
I'm a little confused on like what we're doing or like why.
That is a very fair statement to make. So what we're doing is we're about to see. So I guess I should point this out first. You guys all told me that the derivative, well, maybe you didn't say these words explicitly, but you said in more or less the derivative of the natural log of x is 1 over x. And what I'm showing you now is that you can actually kind of extend that. In fact, I'm going to do something in a minute. So the derivative of the natural log of x is 1 over x. I'm going to show you that the derivative of the natural log of the absolute value of x is also 1 over x. And then I'm going to show you something graphically, and I'm going to use Desmos because my Desmos is much better at graphing than I am. It's just true. So we're kind of in the middle of getting to the understanding place. So hold on for just a sec. So taking the derivative of this, the derivative of the natural log of x is 1 over x. So the derivative of this is 1 over x when x is greater than 0. Okay, the derivative of the natural log of negative x. I'm going to have to use the chain rule. So the way I usually like to say the chain rule is, when I'm taking, like, I know the derivative of the natural log of x is 1 over x. The derivative of the natural log of some stuff is 1 over the stuff. But then what do I have to multiply by?
Negative x or positive x?
Oh, you're very close, except it's not negative x, it's the derivative of negative x. Or more generally, whenever you're using the chain rule, you take the derivative of the outside function, you leave the insides alone, but then you multiply by the derivative of the inside part.
Right.
And so the
Forgot
derivative
about
of
that.
negative x is just -1. But look, these two parts are the same. 1 over negative x times -1 is just 1 over x. So this is just 1 over x, as long as x is not equal to 0. So the takeaway here is that when you're asked to find the antiderivative of 1 over x, or x to the -1, the answer has to be not just the natural log of x, but the natural log of the absolute value of x. And here's a graphical explanation of why. So let me do this. Yeah, great. Share my screen. Where's the thing I want? Sure, you're here. Fine. Great. Cool. Let's do it. So what I want to show you guys is that, so here is good old 1 over x. Right? Nice function. And it's antiderivative. So here's the problem with natural log of just x. I guess I could have a y equals here. So right, this is the, I guess I could give them some better names. Let's call this capital log of x just for fun. All right, so here's the problem. And it's only kind of a problem. 1 over x has a much larger domain than the natural log of x, right? 1 over x, the domain is everything except for 0. And the problem is, basically, if you're saying the antiderivative of 1 over x is natural log of x, you would like to then be able to take the derivative of natural log of x and get back to 1 over x. But the problem is, if your function is just natural log of x, its derivative is 1 over x, but it's 1 over x when x is just greater than 0. And so we don't capture the whole function that we started out with, right? Whereas if we make our antiderivative the natural log of the absolute value of x, it just disappears. Really? Really? You're going to do me like that, Desmos? Come on. Maybe I feel slighted here. Okay, there we go. Okay, it works. All right. So now, if we look at these functions, they have the same domain. Both natural log of the absolute value of x and 1 over x are defined everywhere except for 0. And importantly, the derivative of the natural log of the absolute value of x is the derivative that is equal to 1 over x. So over here on the left side, right, the blue function is the antiderivative. The red function is the function, or the derivative of the blue function. And if you look at this, right, so if you're thinking of this as your original function and the red function as your derivative, the slope of the tangent line here is very slightly negative, and the values here are very slightly negative. The slope of the tangent line over here gets more negative, and the values here get more negative. And then the same sort of thing's happening on the right side. over on the right side, the tangent line here is very positively steep, and the values here are very positive. Over here, the values of the tangent lines have very kind of positive but less steep values. And the red function has, the tangent lines are very, the words are getting a little bit much. Here, the tangent lines are positive but not super big, or the slopes, I should say, that's the word I was reading. And here the corresponding values are positive and not very big. So we need this so that the domains match up. We would, in general, when we take an antiderivative, like its domain to be at least as large as the domain of the original function you're antidifferentiating. There's a couple other examples of that, and here is one of them, just to kind of, off the top of my head. Sorry, let me stop sharing. So another function that's kind of similar, but not nearly as crazy, is we know that the derivative of the inverse sine function, or if you prefer, you can write it as arcsine. These both mean the same thing. Some people like this and people like this. I like this because sometimes people confuse this with 1 over sine, which it is not 1 over sine. It's totally different. But either way, the derivative here is 1 over the square root of 1 minus x squared. And so if I asked, what's the antiderivative of f of x equal to 1 over the square root of 1 minus x squared, well, of course, we would say it's inverse sine of x plus c. We need the plus c. But here's what I want to mention, or what I want to point out. This function, the domain here, is everything between -1 and 1, exclusive of the endpoints, right? You can't plug in 1, so if you plug in 1, you'll get division by 0. And you can't plug in anything bigger than 1, because then you'll have a square root of a negative. And what you may or may not know is that the domain of this function is actually just slightly larger than that. It is -1 to 1 inclusive. And here's what I will point out. I can draw this one. So it might have been a while. But here's what the graph of the inverse sine function looks like. And you can see from the graph that the domain is from -1 to 1. But if you look, if you think about the derivative being 1 over the square root of 1 minus x squared, you can also kind of see that, oh, well, if I get way over here, my tangent lines, right, at the very end here, the tangent line becomes a vertical tangent line. And vertical tangent lines have undefined slopes. So that's why this derivative of this isn't defined at 1 or at -1, because the derivative at that point would be undefined, because the tangent line is a vertical line with an undefined slope. So big picture, typically the antiderivative has the same domain as the function, but sometimes the domain is actually slightly larger. Smaller picture, but more important, the antiderivative of 1 over x is the natural log of the absolute value of x. So I know it was a lot of talking to kind of get to that one point, but that's really what you want to take away from that, is that the antiderivative of f of x equal to either x to the minus first or 1 over x, right, same thing, is the natural log of the absolute value of x plus c. And the absolute value is important. I do say stuff a lot, especially when I'm talking about the chain rule. So let's see, back to the questions. Got about 12 more minutes. Let's see, what else do I want to make sure I point out here? So the idea is that in a lot of ways, anti-differentiation works very similarly to differentiation, just kind of the reverse, meaning that if we have powers of x, we can do nice things. For example, let's say I want to find the antiderivative of, let's use a different letter. Let's say g of x is equal to 1 over x squared plus 3 over x plus 1 over 1 plus x squared. He said 4. Okay, 4. So a couple things to be aware of. Powers are great, meaning I would really like to write this as not x 1 over x squared, but x to the minus 2. Because then I can just apply what I usually call the reverse power rule or the anti-power rule, right? If you're anti-differentiating x to a power, you add 1 to the power and divide by the new power. The only exception is if you've got 1 over x or 3 over x or anything over x. I would generally like to write this as 3 times 1 over x. Because when you have a constant multiple of a thing, I like to think it just kind of hangs out. So if you've got a 3 times your function, the antiderivative is going to be 3 times the antiderivative of that. Just like if you were differentiating 5 times x cubed, we all know the derivative here is 15x squared. But what you're probably, or maybe forgetting that you're doing, is you're really saying, oh, the derivative here is 5 times the derivative of x cubed is 3x squared, and then doing the multiplication. The same thing is happening up here. When I anti-differentiate 3 over x, I'm really saying, oh, it's 3 times the antiderivative of 1 over x, which is going to be natural log of the absolute value of x. And I'm going to do the same thing here. I'm going to pull out this 4, and I'm going to have a 1 over 1 plus x squared. So now we're going to anti-differentiate. And then I'm going to use the corresponding capital letter. Eventually, we'll start using the integral symbol, but we haven't probably done that yet. So it feels like it's kind of getting ahead of ourselves. So I'm going to use the anti-power rule. I'm going to do x to the -2 plus 1 divided by -2 plus 1. As long as I don't get a 0 in the denominator, I'm good to go. Here, I get 3 times the antiderivative of 1 over x. We just talked about a whole lot. It's the natural log of the absolute value of x. And finally, here, the antiderivative of 4 times 1 over 1 plus x squared is 4 times the antiderivative of 1 over 1 plus x squared. So, does anyone know a function whose derivative is 1 over 1 plus x squared?
Tangent or inverse.
Correct.
Sorry, inverse tangent.
Inverse tangent or arctangent. Yes, exactly. The inverse tangent function has a derivative that is 1 over 1 plus x squared. And then plus c. And then the only other thing we should do is we should probably simplify this, right? I should really write this as x to the -1 over -1. And it feels even silly to leave it that way. I would probably write it as either, because dividing by -1 is the same as multiplying by -1. I would write it as -x to the -1 or -1 over x. Either way. Seems like it's hard to see. The rest of it's perfectly fine. I know what I should do. Probably should. I should leave it on that. I'm just going to make a couple problems. So let's say I want to find the antiderivative of h of x equal to x to the fifth plus 2x cubed plus x all over x squared. Let's make that a 4x minus sine of x plus cosecant x cotangent x. Something to be aware of, which people can get nitpicky about, is if I'm finding the antiderivative of this, I kind of have to do it all at once. Meaning, before I can antidifferentiate, I really kind of need to simplify this. So I'm just going to rewrite this as, so I'm dividing each thing by x squared. X to the fifth divided by x squared is x cubed. 2x cubed divided by x squared is 2x. And 4x divided by x squared is 4x to the negative first. And then I'm just going to rewrite these things, right? Because I'm just simplifying this. I'm not actually doing any anti-differentiation yet. But I've definitely seen people write like that this turned into, you know, plus cosine x minus cosecant x to be the antiderivative. But we can't kind of mix and match. We need to do only simplifying or only anti-differentiating in our step. And now we're going to anti-differentiate. So the antiderivative of x cubed is x to the fourth over 4. The antiderivative of 2x is 2x to the second over 2. The antiderivative of 4x to the negative first is 4 times the antiderivative of x to the negative first is the natural log of the opposite value of x. I'll be perfectly honest, I almost always rewrite x to the negative first as 1 over x to remind myself that its antiderivative is the natural log of the opposite value of x. But it is also perfectly legitimate to leave it as x to the negative first and then say its antiderivative is the natural log of the opposite value of x. Okay, whose function has a derivative that is negative sine? Positive cosine. Derivative of cosine is negative sine. Whose derivative is cosecant plus times cotangent? So we know that the derivative of cosecant of x is negative cosecant of x times cotangent of x. So we're going to adjust by a negative sign and say I need a negative cosecant of x here. Because the derivative of negative cosecant would be negative cosecant of x times cotangent of x, which would be positive cosecant x times cotangent x. Time is it? So what I feel like I should say here, yeah, we'll talk about that next time. So I would definitely encourage everyone to look at those kinds of lists of derivatives and antiderivatives. And even though I'm telling you should look at them, I feel like I should say what the trig ones are because the trig ones come up a lot. So we know the derivative of sine of x is cosine of x. And the derivative of cosine of x is negative sine of x. And I'm just going to start using the symbology because it is kind of the easiest way to write things. So this symbol, and we'll talk about this more later, this integral symbol is also used to mean the antiderivative. The antiderivative of cosine of x is sine of x. Let's see. The antiderivative of sine of x is negative cosine of x. And the reason that works is because, well, the derivative of cosine is negative sine. So we can see that the derivative of negative cosine is negative sine, which is just sine. So usually if your derivative or antiderivative is off by a plus or minus symbol, you can adjust for that by just multiplying by the appropriate sign. And it's terrible that the function sign and the word sign sound the same, but they do. So I will try to be very specific when I talk about them. What time is it? Okay. And then we've got 4 other trig functions. So we've got the derivative of tangent equal to secant squared. And so the antiderivative of secant squared is equal to tangent plus c. And let's do cotangent. The derivative of cotangent of x is cosecant squared of x, but it's negative. And so then the antiderivative of cosecant squared of x is negative cotangent of x plus c. Again, the derivative of cotangent is negative cosecant squared. So the derivative of negative cotangent is negative cosecant squared, which is just cosecant squared. Finally, the last 2. The derivative of secant of x is secant x times tangent x. And so the antiderivative of secant x tangent x is just secant of x plus c. And the very last one, the derivative of cosecant of x is cosecant of, my cosecant's always in there funky, is cosecant of x times cotangent of x. The antiderivative of cosecant x, oh, sorry, I forgot a sign. Also, by the way, in case you hadn't noticed this before, for trig functions, the derivatives of the co-functions, cosine, cotangent, cosecant, are all negative. So that's something worth being aware of. And so are the antiderivatives. The antiderivative cosine, oh, sorry, that's not true. Sorry, that's the reverse for the antiderivatives. Apologies. The sine and, no, it's not. There's no good pattern for the antiderivatives. Sorry, I lied. So the antiderivative of cosecant x, cotangent x is negative cosecant of x. Let's see. We will talk about eventually the antiderivative of tangent and cotangent and secant and cosecant, but they're a little more complicated. Sophia.
I was wondering, why do the bottom 3 not have like the dx after it?
Because I'm dumb. Because I forgot it.
Okay. Just wanted to make sure I wasn't missing
That's
something.
a really good point. I am usually quite the stickler for the dx. And the dx just means that it means that x is the variable you're anti-differentiating with respect to. So it's really just part of the instructions. This symbol here says anti-differentiate. And this symbol here says for the variable x. So they're just instructions. Just like this is an instruction that says take the derivative of this function with respect to the variable x. And so then once I've done it, I don't write the instructions anymore. Just like over here, once I've done the antiderivative of secant squared, I don't write the integral symbol anymore. I just write the answer, which is tangent. So yeah. So these are definitely derivatives and antiderivatives you should be very well aware of. Certainly the derivatives, the antiderivatives just come from the fact that we know the derivatives already. So basically, anything you already know how to differentiate, you kind of already know how to anti-differentiate. And so that is like the inverse trig functions, right? If you know the derivative of inverse tangent is 1 over 1 plus x squared, then you know, even if you don't know, that the antiderivative of 1 over 1 plus x squared is inverse tangent. All right, it is past time to be done, so I should stop the class. I will generally try